Okay, we're going to get to the fundamental theorem of calculus in this video. To do that, I just want to state some properties of the integral. I'm not going to prove these. I'll let you guys prove them as an exercise. This is Theorem 6.12 and Theorem 6.13. So let me label that. Okay, so the first things, if f and g are integrable functions on a, b, then the integral from a to b of f plus g dx is equal to the integral from a to b of f dx plus the integral from a to b of g dx. Additionally, if c is a real number, the integral of c times f dx from a to b equals c times the integral from a to b of f dx. So that's kind of the first thing. Okay. Second thing, if f is less than or equal to g on a, b, then the integral from a to b of f dx is less than or equal to the integral from a to b of g dx. That's the second thing. If c is in the interval from a to b, then f is integrable on AC and on CB, and the integral from A to C of f dx plus the integral from C to B of f dx is equal to the integral from a to b f dx. Okay, so you can break it up into parts. The fourth thing, if the absolute value of f is less than m or equal to m on AB, then the integral from a to b of f dx is less than or equal to m times b minus a. The fifth thing is still just stuff for 6.12, but 6.13, the integral, so f times gx is integrable on AB. And the sixth thing, if additionally the absolute value of f is integrable, then the absolute value of the integral of f dx is less than or equal to, from a to b, the integral from a to b of the absolute value of f dx. Okay. Those 6 things I'm going to use their kind of standard things that you see in a calc class. We're going to use 4 for sure, and we're going to use the summation and product one. So the first one and the fourth one we'll definitely use. 2 is pretty common to use as well. But let's now prove the fundamental theorem of calculus, or how calculus and differentiation interact. So, theorem. So we're going to let f be bounded and integrable. The book makes the assumption that all integrable functions are bounded, or within the definition of integrable is bounded, and that's a fine assumption, but I want to make sure that I explicitly state that it's bounded, because eventually we'll talk about improper integrals in most high school calc classes, and those are integrals that don't happen to have functions that are bounded sometimes on the interval from a to b. Let capital F of x be the integral from a to x of little f of x dx. I'm going to use a different variable so that I can use x as an input variable instead of an integral of, or a variable of integration. Okay, so this is valid by our theorem 6.12 because x is between a and b for x in AB. Okay. Then the conclusion is then f is continuous on AB, and if little f is continuous at x naught, f prime at x naught equals little f at x naught. So not only is f prime differentiable at x naught, we know what the derivative is compared to f. So this is the fundamental theorem of calculus. This is the connection between integration and differentiation. At least this is the first part of it in most books. So this is the fundamental theorem of calculus, part 1. Okay, so let's prove this. We have to prove two things. We have to prove it's continuous, and then we have to prove that it's differentiable if little f is continuous. So, proof. Well, let's draw a picture first. What are we going to do here? So here's our picture from A to B. Now, f is bounded. Let's say this is the bound on little f. Let's say that's capital M. Then the integral from a to x, let's say this is at x here, would be this area. This would be f of x, right? And f of x changes continuously because if I change the input a little bit, the output changes a little bit. How much can the output change? Well, the output change a little bit, so if I change x by a little bit, so I kind of go left or right a little bit, the output can change just by at most m times that change in input. That's going to give me continuity. It's going to actually give me uniform continuity. We're going to say let epsilon be bigger than 0 and let delta equal epsilon over m. If delta changes by epsilon over m, the area change, the epsilon from the function, the actual area change, is at most epsilon then, because the width of this change is at most epsilon over m, the height of the change is at most m, the total change would be at most epsilon. So that's going to be how we get continuity. And a very similar picture is going to be how we get differentiability too. Right? So differentiability is how much exactly does it change, and how much exactly does it change is basically the same thing, right? This changes as the width of this pink rectangle gets smaller. The change divided by the width of the rectangle gets closer and closer to this value f of x when f is continuous there, right? If there was a jump there, then maybe I would have sort of a rectangle up here and a rectangle over here on the left, and I wouldn't know exactly what that average value would be. But since it's smooth, that rate of change is exactly what little f of x is. So this picture kind of says why it's continuous and why the fundamental theorem of calculus works. Let's actually go through the math now. So proof. Okay. Since f is bounded, say absolute value of f is less than m. For all x in AB, put f of x here. Then the magnitude of capital F of y minus little f of x in absolute value, well, that's going to be equal to this integral from a to y of f dx, f dt, right, minus the integral from a to x of f dt, which by 6.12 we can rearrange to be the integral from x to y f dt is at most m times y minus x. Right? As long as, well, let's just take absolute values on all of this stuff. Okay. So, given epsilon bigger than 0, if delta is less than or equal, let's just say equal to epsilon over m, whenever absolute value of y minus x is less than epsilon over m, this statement above here, right, this guy is less than or equal to this guy, we get capital F of y minus capital F of x in absolute value is less than or equal to m times absolute value of y minus x, which is strictly less than epsilon over m times m equals epsilon. Proves continuity. In fact, it proves uniform continuity, right? The same delta did not depend on x at all. It only depended on epsilon, so we actually have uniform continuity here. Of capital F. Okay, now let's do the derivative part. So suppose little f is continuous at x naught. Let epsilon be bigger than 0 and delta be such that whenever a less than or equal to s less than or equal to x naught less than or equal to t less than b, and s comma t are in the neighborhood of size delta around x. Okay, so that's a lot of statements, but the number line is easier to see. So here's a and b, here's x naught. I've got the delta that makes the outputs of x naught close to the output of x naught, and I just want s and t in here. The delta could be big enough to send me outside of a. Say maybe my delta was like this. I still want s and t to be inside the closed interval, so I want to sort of restrict where s and t are. They have to be between a and b, and they have to be close to x. That's what these two statements say. I also want s on the left hand side or equal to x naught, and t on the right hand side. Okay. Then we want to show differentiation, and we have a option, or we have a candidate for what the derivative should be. So f prime at x naught is equal to f at x if we can show that f of t minus f of s over s minus t minus f at x naught gets small, goes to 0, right? That's the definition of derivative, that this limit exists and it's equal to f prime at x naught, or little f at x naught. Okay, so let's look at this left hand side. So let's take f of t minus f of x over s minus t minus f of x naught. Okay, this is equal to the absolute value of 1 over s minus t times the integral. Well, I've got this top part here, this integral. This would be the integral from a to t and a to s, but we've already sort of seen how that works. I can go from s to t of f of x dx. Right, so this piece is equal to this stuff, and then the 1 over s minus t is still in the denominator. Okay, and then I can subtract off f of x naught, put that in absolute value. Okay, so this is also equal to 1 over s minus t in absolute value, and I'm going to bring this constant inside the integral. So I've got f of x minus f of x naught dx, and that's still equality. Okay, so I've got a constant times the length of the integral. The length of the integral is t minus s, which I should be putting all of these things being t minus s. Okay, so we're just gonna so the length of the interval that I'm integrating on is t minus s, and I'm integrating a constant on there. So I've just got a pure rectangle. If I take that rectangle t minus s times f of x naught, and then I divide it by its length, I get the height. And the height is just f of x naught, which goes there if I pull it outside the integral. So this is a true statement now, and I'm going to put this together inside the integral. Okay, and now this is less than or equal to 1 over t minus s times the integral from t to s. Well, f of x and f of x naught are really close together whenever I'm between s and t, because s and t are inside the neighborhood, the delta neighborhood of x naught, right? So we've got these guys inside the delta neighborhood. I had forgotten to put up here that then the absolute value of f of s minus f of t is less than epsilon. Right, that was just using the continuity, right? Okay, so now I'm gonna, oops, and that's not capital, that's lowercase, because I'm using continuity of the little guy. Okay, so using continuity of the little guy, I get that this stuff inside here is smaller than epsilon in absolute value. Alright, and so strictly smaller than actually, right? And so then this is equal to 1 over t minus s times t minus s times epsilon, because I'm just integrating a constant, is equal to epsilon. Okay, what that shows is this guy goes to 0 as s and t get close together. So f prime at x naught equals little f at x naught. And that's our fundamental theorem of calculus, part 1.